All right, welcome to Chapter 4, problems from the textbook. This is question 5. These are scenarios A, B, and C. And it wants to rank the final velocity of the object. So what I like about this one is that in each of these cases, you can see the launch angle is the same. So launch angle, launch angle, launch angle. I'm within my ability to draw it, but the textbook's a little better. So which one hits the ground moving the fastest? Obviously, A hits the ground going the fastest because the ball was in the air the longest, and so it had the most time to speed up in the vertical direction. So in each of these, the horizontal speed is the same. Horizontal speed, horizontal speed, horizontal speed. This one fell the longest from its highest point, so it's going to be long. This one, smaller. And this one, very small. And so when you look at those, and we find the resultant, longest, medium, shortest. Okay, let's do question 9. Okay. In question 9, it gives another kind of graph-looking thing. It's actually a picture of a projectile. So we have a projectile here. And we'll call that 1. And then 2. Oh, this green is garbage. Let's see if there's no green. Oh, there's no greens. No, let's have to do. Let's get pink will do. We'll call that 2. And then use the brown for 3. Okay. And question 9 says, rank them time of flight, initial vertical velocity component, horizontal velocity component, and initial speed. Okay, so time. Okay. So time of flight, 1 = 2 = 3. That's because it's the vertical that determines how much time you're in the air. Since they all went to the same height, they all take the same amount of time in the air. B says, basically the V0y, so the initial vertical velocity component for each. Well, what's cool about this is because they all end up at the same height, they all have the same initial vertical velocity component. 1 = 2 = 3. Horizontal velocity component, so we need the v in the x direction. Now, it's not v0x because the vx is constant the whole time, so it's just vx. And what do we notice about these? Well, which one is going the farthest or fastest to the right? Clearly, this is 3, 2, 1. So 3 is the fastest, okay? 2 and then 1. And then last part says initial speed greatest first. Initial speed greatest first. Well, what I like about this is if you look at the blue one, okay, so here's the blue one. It has this vertical velocity component and a small horizontal velocity component. So therefore, okay, well, let's do the pink one. The pink one has the same vertical velocity component, but a larger horizontal velocity component. And the brown one and so those are the components, all verticals are the same. The horizontals look like this. And so There's the brown. There's the pink. Here's the blue. So we can see that the greatest speed is clearly the brown one. It's number 3. Okay, we are moving on to question 11, which is very hard to draw. There's no way I'm going to be able to draw this. Oh, that was garbage. Okay, that's curve 2. There's curve 3. Which is orange. See if I have orange that works good. Okay. Now, you obviously can see those in the textbook, but this is what they look like. So 1, 2, 3, and 4. Okay. 4, 3, 2, and 1. Oh, one's already up. Cool. So, question is, train moves at a constant speed. Rank the accelerations greatest first. All right. So here's the thing. They're all moving around a circular curve. If you're going around a circle, you have some centripetal acceleration. That's acceleration toward the middle. Okay? And so that centripetal acceleration, AC, C stands for centripetal, that means toward the center, is equal to V squared divided by R. It says they're all going at the same speed, therefore, it's the radius that dictates the amount of acceleration. Since the radius is in the bottom, bigger radius would be smaller acceleration, or smaller radius would be bigger acceleration. So, as the radius value goes up, the acceleration value goes down. Now that's true as long as the speed's constant, and that's what we have here. So, if I rank them greatest first, okay, I would say that 2, and then 1 is equal to 4, and then 3. So if you look at the picture, 2 has the smallest radius, 1 and 4 have the same size radius, not according to my picture, but the textbook picture, and 3 has the largest radius, therefore it has the smallest acceleration. You can actually feel this if you're in a car. If you're going around a turn, if you take a really tight turn, you can really feel that acceleration. If you take a super wide turn, right, it doesn't feel as exciting because the acceleration is so much less. Yeah, it looks like we're moving on to problem 23. Problem 23. Okay. So it says, a projectile is launched from a gun. All right. right, so a projectile is launched from a gun. It's 45 meters above the ground. At a speed of 250 meters per second. Yikesers! So this speed out of the gun is 250 meters per second. Now, I put a V there, but what direction is this V? It's fired directly horizontal, so this is actually going to be our Vx. That's our horizontal velocity. Okay, how long does it take to remain in the air? At what horizontal distance does it strike the ground? And what is the magnitude of the vertical component of its velocity as it strikes the ground? No problem. Now, obviously this isn't going to be to scale, because this is like, this thing's coming out at 250 meters per second. But it's going to come out like this. Okay, and it's going to strike the ground here. Okay, again, not to scale, but we'll get the gist here. So, whenever we're doing a projectile motion problem, we have to break it up into its horizontal and vertical pieces. Okay, its horizontal and vertical pieces. So, all right, when I think about the horizontal, I'm thinking about the horizontal displacement, the horizontal velocity, and the time. When I'm thinking about the vertical, I'm thinking about the vertical displacement, the initial vertical velocity, the final vertical velocity, the acceleration, and the time. So there's a couple of these we know, so let's put in what we know. We don't know how far it went. That would actually be this distance right here. This is actually what we're going to end up solving for in a minute. So we don't know that. We don't know the time. We do know this is 250. What about the vertical? Well, how far did it fall? It started up here. It fell to here. That's 45 meters. Therefore, the change in the vertical position is negative 45 because you do final minus initial. 0 minus 45 is negative 45 meters. Okay? This is the important part here. What is the velocity at time 0 in the y direction? Well, our object is not shot up, it's not shot down, it's only shot horizontally. Therefore, the velocity at time 0 in the y direction is equal to 0. And this is the key to understanding this problem. If your velocity in the y direction is 0, then the rest becomes really easy. We don't know this. We're going to solve for this later. We'll put a question mark. In the vertical direction, it's in free fall. Therefore, your acceleration is baby g, negative 10. And we don't know the time. But we can plug and chug this now. Okay, so let's do the vertical first. Delta y is 1/2 gt squared plus v0yt. This is negative 45. This is negative 5t squared plus, and this is why this problem is easy, because our velocity at time 0 in the y direction is 0. This whole term goes away. Divide both sides by negative 5 and square root. T is equal to 3 seconds. So I'm going to put in 3 seconds here. But the cool part is this is also the same time, so I have 3 seconds there. And now I can figure out how far it went. So, because the horizontal is constant speed, I use rate times time equals distance formula. Now, you're going to look in the textbook, and it's not going to say 3. It's going to say like 3.01 or something like. They're going to use two things. They're going to use significant digits, and they're going to use their g value. Instead of negative 10, they're going to use negative 9.81. It's fine, but your answers are going to be a little bit off due to both those considerations. So the question was, how long does it take to reach the ground? 3 seconds. How far did it go horizontally? 750 meters. And then what is the value of the vertical component? Well, what I like about this is when it hits the ground here, okay, it's moving to the right at 250 meters per second, because that's constant. And what about the vertical? How fast is it moving in the vertical direction? Well, there's a couple ways to do it. We can reason it out, okay? Or we can use the equation. Let's do the equation first. We know that the vertical velocity is equal to the acceleration times time plus the initial vertical velocity. We know that's a thing. So if I want to find this, negative 10 times 3 plus 0 again, don't forget that. So the initial vertical velocity is negative 30 meters per second, which is the answer. If I go put that in here, it's a small amount. Okay? But we can also just reason it. In the vertical direction, it starts with initial velocity of 0 and it falls for 3 seconds. If the velocity changes by negative 10 each second, after 1 second, negative 10, after 2 seconds, negative 20, and after 3 seconds, negative 30, which we got. If you wanted to do the resultant velocity for this, it doesn't ask, but in case you wanted to, we could use little Pythagorean theorem to get the diagonal. That is the resultant velocity. And if you wanted to, you could get the angle. That's great. Okay, we'll move on to problem 25. P25. Okay. It says the current world record motorcycle jump. So let's say you're on your motorcycle and you're here. Okay? I think it says it's like 77 meters. Okay? So 77 meters, and it leaves the ground at an angle of 12 degrees. Okay? No problem. So this angle here, which is this angle here, is 12 degrees. And this is 77 meters. Okay. Well, again, in order to do this problem, any projectile problem, I'm going to break it up into its horizontal and vertical components. All right, so let's talk about, actually before we even talk about that, let's see what's going on with the launch itself. So what I have is I have this here. So when he leaves, I know at a 12-degree angle is the initial velocity. But it's moving horizontally and vertically at the same time. So in the horizontal direction, we have this. That's the v in the x direction. In the vertical direction, we have this. That's the v0 in the y direction. Now again, we call this one v0 in the y because that's the initial. It changes over time. This is what it is at time 0. The vx doesn't change over time, so we just call it vx. All right, here's our angle here. In this case, it's 12 degrees. We'll call it theta. We know it's 12 degrees. All right. I think we're trying to find the v0. Does it say what's the launch speed? Yep. So let's consider the horizontal and vertical motions independently. So here's the horizontal. I know delta x, vx, and t. Those are the things that we are looking for. I know this is 77. I don't know this yet, and I don't know this yet. We may be able to express this in terms of that, but let's not get excited. Let's do the vertical. So here's the vertical. We know we have vertical displacement, initial vertical velocity, final vertical velocity, acceleration, and time. Get rid of this. Okay. So where we're at up here is, how do I relate these four, or three of the four of these things at one time? Well, the Vx, let's do the Vx first. Relative to this angle, the Vx is the adjacent side. and the V0 is the hypotenuse. So given that construct, I can say that the Vx is equal to the V0 times the cosine of my angle. That means that this one over here is the opposite side. Now I drew it here, but you could just as easily draw it here. That would be the opposite side. So the V0y is equal to V0 times the sine of theta. Okay? So can I put those in here, and is that going to help us? It's probably going to help us because of the fact that we actually need to solve for this V0 right here. Okay. So let me put it in for the blue. This is V0 cosine. Now it's V0 cosine 12. You know the angle's 12 there. This is then V0 sine 12. We don't know what this is. We know this is negative 10 meters per second. That's my baby G. What about the delta y? This is really the interesting part about this problem is what's the delta y value? Well, what's cool is that you start at this height here and then you end at the same height there. So even though you go some height up and then come down, what is the change in your vertical position? It's 0 because you landed where you ended. So even if this was like 10 feet off the ground and this was 10, 10 minus 10 is still 0. So that's 0 meters. Now this makes this part easy. We can probably solve for the t, or maybe we'll have to do some substitution here. Let's look actually, because that's probably interesting. This one, we know delta x is equal to vxt. So 77 is equal to v0 cosine 12 t. Okay. Now in here, there's two variables, which means I can't solve it if there's two variables, not by itself. I'm going to do this one up here. Okay. There's our parent equation. I know this is 0. This is negative 5t squared plus v0 sine 12t. So I like where we're at right now because I have this equation with two variables and this equation with two variables. And if I have two equations and two variables, then I can put them together and solve. Now how you do that is up to you. First thing I'm going to do is I'm going to divide a t out of each of these. So divide by t, divide by t, divide by t. All right, and then I have 0 is equal to negative 5t plus v0 sine 12. Is that cool? So if I solve this one for t, and I solve this one for t, I could set them both equal to each other. This is a fine way to do it. I'll show you how this works. So t here is going to be equal to v0 sine 12 all over 5. I added this term to both sides and then divided both sides by 5. If I want to solve for t in this one, it's going to be 77 divided by v0 sine 12. So this is t and this is t. I'm going to set those two things equal to each other. By doing that, we actually get rid of the t and we can solve for v0 directly, which is cool. You could have solved for this t and put it into this equation. It's the same thing. It doesn't matter. All right, so let me write them together here.